All right, what's going on, ladies and gentlemen? Hope you're doing fantastic. I know I can't see you, but I'm sure it is great to see your smiling faces once again. All right, we are diving into the second half of 6.1. I'm going to break this up into three sections now, or three parts now, instead of just two. So a couple examples for today. The ultimate goal of this video is to be able to do what we call resolve a vector. And the main part is to be able to find the direction angle of a vector. Let's start off with this. You guys hopefully all remember the unit circle. And you remember that the horizontal component of the unit circle was cosine, and the vertical component was sine. And hopefully you also recall that the unit circle is a unit circle because of its radii that are all 1. And what this does is it allows us to connect vectors to the unit circle or vectors to trigonometry. So if the radii of a unit circle was a vector, it would be a vector with a magnitude of what? Hopefully you realize it's a vector of a magnitude of 1. And if the vector has a magnitude of 1, and every horizontal component is the cosine ratio, and every vertical component is the sine ratio, there is a direct connection between the vector, aka the radii, and the cosine and sine of a unit circle. What about if it wasn't a part of a unit circle? What if the vector didn't have a magnitude of 1? What if the radii didn't have a radius of 1? Well, what ends up happening is we have a way to do what we call resolve a vector. And ultimately what that is utilizing trigonometry to show the components of a vector utilizing cosine and sine of a specific angle. What angle? We call that angle the direction angle. The direction in which the vector is pointing from the positive x-axis, right? The connection, if the positive x-axis was the initial side of the angle created, the vector is the terminal side of the angle that is created. And ultimately, we can make that connection to the vector and its components, horizontal and vertical, to the trigonometric horizontal and vertical components, cosine and sine, respectively. And so that's what we're going to go ahead and do in this very first example, example 5. So directly from your notes packets here. Very basic to get things started. We are basically going to just take what we now know about resolving a vector, that it's a direct connection to the magnitude of the vector, the size of the vector, and the horizontal component cosine and the vertical component sine. So it says find the components of the vector v with direction angle 115 degrees and a magnitude of 6 using no technology except when we need to approximate the exact trig value. So super simple to get things going. We're basically just trying to say, hey, I know that vectors are written in the component form a comma b, horizontal moving left and right, vertical moving up and down. But what about, can I utilize information about a vector's direction angle, like the fact that it has a 115 degree direction angle, so 115 degree direction angle, and the magnitude of 6. Take that information and figure out what the left, right, up, down components are of the vector. So the vector can then be rewritten as the magnitude 6 times the cosine of the direction, 115, and 6 times the sine of the direction angle, 115. And that's it. Other than just plugging it into your calculator and identifying what the values actually come on out to be. So we get 6 cosine 115 and 6 sine 115. And so we end up with about negative 2.4 comma 5.44. Okay, so about negative 2.5 to the left and about 5.5 up. That makes sense because a negative horizontal component and a positive vertical component should hang out in quadrant 2. That's exactly what it did. Okay, so that's resolving a vector. Now let's actually work backwards now and find the direction angle of the vector. We've got a vector now. We have the a comma b components. Now we're just trying to figure out what angle gets created by said vector of moving 3 units right and 2 units up to get from the start to the end of the vector. Well, the number one thing, you can write this down, is when you're trying to find out the direction angle, is to identify what quadrant the vector is in. So first and foremost, 3 comma 2, right? Positive x component, positive y component. It's not a point necessarily, it's a movement, all right? But that movement puts us in quadrant 1. And so both the cosine inverse and the sine inverse's restricted domains should not be affected, okay? Let's go ahead and find first and foremost what it says is the magnitude. So we'll find the magnitude of u. Remember, the magnitude is the square root of the a component squared plus the b component squared. And so we get the square root of 9 plus 4, so 13. And so then ultimately we can rewrite u to be the square root of 13 times the cosine of theta times the square root of 13 times the sine of theta. Now you might be saying, well, what are we doing this for? You're making it more complicated. Yeah, but we have a goal. The goal is to find the direction angle. And we're going to take what we now know, because remember, this horizontal component already had a value. The value is 3. The vertical component already had a value. It's 2. So I don't care which one you choose. Choose one of them and set it equal to its respective value. I usually tend to use the cosine one just because it kind of usually doesn't get us into too big of an issue when you do the inverses. But sometimes you may want to do the vertical component, but it doesn't overly matter which one you set it equal to. We're going to set square root of 13 cosine theta equal to its respective horizontal component 3. We're going to divide through. So we get 3 over square root of 13. And we get theta is equal to cosine inverse of 3 over root 13. So second cosine 3 over root 13. Now it just makes me feel better to kind of close up the parentheses. You get about 33.69, and that makes sense. We're in quadrant 1. This is an acute angle in quadrant 1. This makes sense. 33.69 degrees. So let me just kind of refer to you what this is showing. This is showing that we just found this vector 3, 2 had a magnitude of the square root of 13 and had a direction angle of 33.69. That's what we just overall found and how we can interpret it. All right, well, I challenge you to pause the video and try part B on your own, then obviously pick the video back on up when you want to see how you did. So we want to go ahead and find the magnitude first and foremost. The magnitude of V is going to be negative 2 squared plus negative 5 squared, all underneath that square root. So we get 25 plus 4, so root 29. And if you remember, what was the first thing I said I should always check? Check to identify what quadrant the vector is going to be in. It's going to be very beneficial for us. This is in quadrant 3. These are interesting. These are a little bit more of a doozy just because the restricted domain for inverse sine is negative pi halves to pi halves to the right side of the unit circle. Restricted domain for cosine inverse is going to be from 0 on to pi. And so that's the top half of it. This is quadrant 3. This doesn't accumulate any of them. So we have to take that into account, whether we use cosine or sine. So let's go ahead and take a look here. We now know that square root of 29 times the cosine of theta, square root 29 times the sine of theta, is equal to -2, -5. So that means that root 29 times cosine theta equals -2. Now I'm going to use the cosine theta here. You don't really have to. In my opinion, sometimes hanging out in quadrant 3 using cosine makes a little bit more sense, and usually students understand it a little bit better. So I'm going to go ahead and utilize root 29 cosine theta equals -2. So once we divide through and take the inverse, you see that cosine inverse is -2 over root 29. So when you take -2, so second cosine -2, second root, division sign would help, huh? Divided by root 29. Look at what happens here. You get 111. Well, 111 is not in quadrant 3. 111 is in quadrant 2. But we know that a vector that is going to have -2, -5 is going to be in quadrant 3. So a couple ways you can go about this, okay? Since we're dealing with cosine here, you take 360 and subtract the value that you just got, and it's going to put you in the complete, not opposite, it's a bad way of saying opposite, but it's going to put you all the way around the circle with the exception of the number that you just got. So that's going to give us a good spot. Or you could find the difference of 111.8 from 180 and then re-add it back to 180. So either way, it ends up working. But 111.8 degrees is not the value because it's in quadrant 3. 360 degrees minus 111.8 is your value, and you get 360 minus 111.8, you can get about 248.2 degrees. Now that makes sense. That's hanging out in quadrant 3. That is in between 180 and 270. So that's all I've got for this video, folks. Hopefully you were able to follow along. And on to the next one.